So on the left hand side here, we have opened an MPlus output file which includes our linear regression. So we see that the variables we're going to use are personal and professional fulfillment and health. So these here are variables in the data set, and then we specify them here again as the variables we are going to use, and this is our regression model. Now, the way you actually write this in equation form would be something like scores on health for individual I are a function of some intercept of health. So this is the level of health you expect a person to have if they have a score of 0 on both personal and professional fulfillment. So that's the intercept. Let's mark it here in red. Okay, plus some beta 1 times their scores on professional fulfillment. So that's for individual I. Plus another beta, let's call this beta 2, times scores on personal fulfillment, again for individual I, plus some error. And this is again individual specific. So in fact you would actually write this in a single line, and this is why a lot of people prefer to write the syntax here in a different kind of way. They just prefer to condense it and say health on, and then put all predictors here, prof, pers, and then close it with a semicolon. So you can use that notation if you prefer it. In any case, let's have a look at where we find these different things. So we'll also have the slopes here. So these are the two slopes, one for each predictor, and then we also have this here, which in the model we will see in the form of the residual variance. This is the bit of information that suggests there's noise in our data. So when you obtain scores on health, they're not just a function of the intercept and of professional and personal fulfillment, they're also a function of the error. So let's have a look at this. And you see here that you get this sample statistics table. This actually might come in handy when we look at things specifically, because we will need things like mean levels, say for the predictors. But we might also need variances or covariances. Let's scroll all the way down to the model, and let's have a look at the unstandardized results, which I'm going to highlight here. Right, so we have these two regression coefficients here, and we also have the intercept. Let's see if we can identify what they should be. So let's first call these beta 1, beta 2, and then this would be beta 0. And let's have a look at the mathematical formula for them. So if we wanted to compute beta 1 using OLS regression, we would take the correlation between health and prof, and then we would multiply that by the standard deviation of health over the standard deviation of prof. Okay, so in order to obtain that information, it's actually easier to look at a different kind of model, and I've put this model here on the right hand side, so let's have a look at it. So in this model here, you see that you have the same data set and you have the same variables, but you don't have a model command, and instead what you have over there is the analysis command, and you just say type equals basic, which will produce different kinds of results. So if I run this model and I scroll down, you will notice that we don't actually have any regression coefficients because we didn't specify a model. So what we have are estimated sample statistics. This includes means, covariances and correlations, And in the univariate sample statistics, we have means and variances. So let's see what we need from here. First of all, we need the correlation between health and professional fulfillment, which you will find in that table over there. So it's 0.539, and we will try to multiply that by the standard deviation. So now the standard deviation can be found in the table below, and the standard deviation is just the root square of the variance. It's always the case, that's how these two are defined. If you look at the table down below, you will see that the variance for health is 1.737, it's just the last number there. And you want to divide this by the standard deviation, so the root of the variance for professional fulfillment, which is 1.072. So, by the way, if you want the information about the variance, you can also obtain it from your regression output. It's actually up here in this table. So you see the variance is here, and for health it's this, and then for professional fulfillment it's this. But I think it's easier to look at the type equals basic version. Right, so let me put this into my calculator, and I'll give you a second to put this into your calculator, and let's see what number it is we get. So the number I got here is 0.686, and this should be the number that you see over here. But you see, it's not exactly that number, so maybe we have a problem. And in fact, we kind of do have a problem. We did not actually run OLS. We estimated our parameters using maximum likelihood instead of OLS. So the formula changes a bit, and the formula for ML is actually rather different. It goes like this. Let's choose a different color. For beta 1, you need to divide the covariance between health and professional fulfillment by the variance of professional fulfillment. Okay, so how would this work? Let's look at the covariance in our other file. So the covariance is up here in this table, and it is 0.736, and we divide that by the variance of prof, which is 1.072. So let's have a quick look at what we get here. So I put this into my calculator, and the number I got was 0.686. So if you look at both of these, you notice that are actually the same number. This is actually true. The estimates produced by OLS and the estimates produced by ML happen to be the same. But the biggest problem is that neither of them is this number, which is what we were looking for. Now, if you do the same for beta 2, the other regression coefficient, you will find the same thing. So first of all, what we've learned so far is that we're not actually doing OLS, we're doing ML. Now, what is this ML thing, and why don't our coefficients match from what we computed by hand? Well, because there's a second subtlety, which is that we are not actually calculating these regression coefficients directly from the equation, but rather we are calculating them in an iterative process in which the best possible estimate is produced. So, in fact, we don't usually just take the regression and plug in the numbers and then that's it, because when you look at this output file here on the right, you see that these things here are actually estimated sample statistics. So it means that these sample statistics were themselves estimated rather than true. So let's dig a little bit deeper. When you have this regression equation, first of all, what you need to know is that we are using an estimation based on maximum likelihood, not ordinary least squares. This is how it's done in M+. But of course you're still wondering, what is this ML and why don't my calculations coincide? Now, in order to explain ML, you would need a bunch of mathematics. So you would need to understand rules of logarithms. You would need to understand matrices and matrix manipulation. You would need to know some calculus to be able to take derivatives and partial derivatives. You would also need to understand a bit of probability, so a bit of statistics in a mathematical sense. And therefore we won't go into the details of what happens, but I want to give you just a bit of an indication. It goes like this. We assume that we have drawn a random sample, so I'll just write it here where there's a bit of space. From a general population, we have drawn just a tiny random sample, even though our population is much bigger and it's kind of unknown. And we have decided that our random sample represents the population and our variables are related in a certain way. So what we're doing here is we're not making inferences from the data to the model parameters, but rather we are trying multiple models and we are choosing the one that increases the likelihood of the observed data or data patterns. So this is really what we're doing, and we're not doing this. And I think this is what's really hard to grasp, is that we're actually trying to relate these variables via the relationships we specified, which are basically these regression components here, including this one and including this one. And we're trying to find the coefficients here that maximize the likelihood of observing a certain pattern of scores for this, for this, for this. Or rather, perhaps it's better to say a certain pattern of variances and covariances. So in any case, we are trying multiple versions of these coefficients that maximize the likelihood of obtaining the data that we have. And this is why it's called maximum likelihood. Now, this relies on several assumptions, perhaps the most important of which is the normal distribution of the residuals. So when your data is of a different type, so for example your outcome variables might not be continuous and normally distributed, well, in those cases we might use other estimators. And this is what really changes when you have different types of data. So in the next videos I will show you how you modify a regression when your outcome variable is skewed but still continuous, and when your outcome variable is categorical. We will also have an example where the outcome variable is of the type count, for example, how many crimes. I hope this was in some ways helpful to you. You can tell that it's very difficult to bridge a gap between maximum likelihood estimation as a mathematical technique and an intuitive understanding of how it's used. So I hope I have managed to bring some clarity or some intuition in that respect. For those of you who know how to take partial derivatives and have seen things like this before, I have suggested a video in a link below. So have a look at that video. It's on YouTube and it's a fantastic video. It's really, really nice. It's on a slightly simpler case, but perhaps it will really help open the door towards maximum likelihood. So let's have a look at different types of regressions and how to specify them in MPlus.